Yes, today's lab is going to be, we're going to write some C code, not C++, pure, C code, not C++ code. C, for the most part, is a subset of C++, so if you know how to do C code, if you know how to do C++ code, for the most part, you know how to do C code already. Alright, we got about 3 more minutes. And in the general channel, there has been a little bit of an interesting discussion about what's going to be in the test, what kind of question will be in our test. So, if you missed that discussion in a general text channel, you might want to go check it out.
Will float points be on the test, or is it mostly going to be subtraction?
No, floating point will not be in exam 1. I have to be very specific, because if I say no and I put it into exam 2, then somebody is gonna say, "But Tech, you said this is not going to be in the test, but that was in the context of exam 1, but you didn't say exam 1, so now I'm saying exam 1." And just as a reference, the there are certain lawyers that are paid a whole lot more than just developers. Those are the patent lawyers. So if someone in this class, thinks, "Hey, I'm actually pretty good as a lawyer," you might want to get a computer science degree first, and then go get a JD, and then become a patent lawyer. Those are the lawyers making the big bucks. Alright, so Caleb says, is the lab just implementing EXP10 to EXP2? Yes, and only when the exponent of 10 is negative. So it's very specific, and the requirement is not even to do a full double floating point number conversion. It's really just getting most of it done. Okay, so there's one last part where we put all the pieces together. That part is not even done in the lab. I'll describe it when we get to it. Alright, so yep, there are people who are still not using their apps.lostreals.edu account to try to join the meeting, and so I have to admit those people one by one.
I just tell people to go figure out how to use their student email.
Well, I'm assuming everybody knows how to use their student account, because with your other classes, every other class will use the student email for contact purposes. So that's kind of important. All right, we got 30 more seconds to go, and there are no questions whatsoever. Well, I can mention something that happened today. I was in a meeting. It's a district-wide meeting, meaning all 4 colleges has people in it, and they're all faculty. They're all professors. And the topic was Proctorio. As a proctoring software / system, we are the district has been paying money for that service, and the contract is running out soon. And so the question is, what should we be doing now? Should we continue with Proctorio? Should we switch to ProctorU? And so on and so forth. And I basically said, there's no point. There's no point in using proctoring software. They're all pretty much defeatable. And a few people did not want to hear that. It's like, la 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 la. I'm not hearing this. Well, if you use a second device, some proctoring software would use eye movement tracking and then AI, they probably train a neural net, to do this, to basically, identify, eye movement, looking at something off the screen. But if you have pets or children, okay, um, you probably will look off screen, at some point, during an assessment, unless you lock out everything, right? So, that doesn't seem to work. Exactly. Yep. I agree with Omer that it does add stress to the students. It's not extra work for the teacher because, according to Proctorial, they use their AI to identify cases, so which is not entirely always accurate. And then Andrew says, the psychological impact of the home becoming a site of surveillance. um, that is true. That's why a lot of professors don't turn on the webcam, but they do screen recording. So what Caleb says, that it actually has a technical term now. The technical term is called authentic assessment. It's called authentic assessment, which refers to tests that are not based on test banks that come with books and publishers. Um, and Chris, you're not the only one. I mean, if you look into my background, it's really cluttered. Not that I'm proud of it, but that's life. Yeah, you can bring the two cats. If your eye starts to go off screen and Proctorial says, "Hey, your eye is off screen," you just go like, "Wait, but this is why I got cats." There. Yeah. Oh, I think Omar is bringing up a very interesting point. Facial recognition using neural nets, um, has potential issues of being biased, and I'm guessing it is biased based on facial features and skin colors. Cool. All right, so with almost everybody here, I'm gonna get today's class started. What you see here on the screen is the fingering. That's funny. Um, so what you see on the screen here is basically tonight's lab. It's not open yet. You cannot see it just yet. Okay. So what we'll do is we're gonna go over this, and let me see if I can. That's the default font size. It's a little bit small. I'm gonna bump it up a little bit like that. So there are two links that you can use to download something. Well, there are three links. One link is this one over here in the question. So what you see is quote unquote this link. This is an archive. That's a zip file. Okay, that's all it is. It's just a zip file. If you already have code blocks installed and you like code blocks and you know how to get around in code blocks, that is one route to do this. On the other hand, if you say, I don't want to install anything on my computer other than the browser that comes with it, then you can go ahead and use Online GDB, which I have used in this class several times already. So we'll go ahead and go to onlinegdb.com. And this is Online GDB. All you have to do, you don't even have to set up an account to use Online GDB. But if you don't have an account, then there's no way for you to quote unquote save your files. I can save my files because I already have an account on with Online GDB. I'm not sure about Replit. Whether it will probably work too. Replit will probably work in this case because I have one version of the program that doesn't need to include any of the local header files. So if you go all the way to the beginning, or just look under the pinned messages, the first one down the list is an attachment called main.c. So that one is a single source file. Instead of using header files and other source files, it is a single file that you can use for tonight's lab. So that's kind of convenient for people who want to use Replit. Sea Lion. Okay, so whatever you guys want to do. Okay, that's entirely up to you. Okay, you can use an IDE that's installed on your computer. You can also just go ahead and use the single source file. So I'm going to use the single source file because that is that's I mean that's the easiest way to do it. So with a single source file, I'm going to copy it first to my clipboard, and then I'll copy the whole thing into the browser. So I'm going to do a few things off screen. Okay. All right, so that's that. And now I can paste the entire program here. So that's gonna be your starting point. So there are a few things that you need to kind of read first, to make sure you understand how the program is structured. But the bottom line is there is a subroutine called exp10, which is exponent of 10, to exp2, which is exponent of 2. So this is the subroutine that you have to put in your logic, and that's the only thing you have to do. You don't have to touch the rest of this program. I'm just reading the text channel here. Okay, so there's nothing going on over there. Okay, so this program, when you run this program, it does take a little bit of extra. You need to know how to run this program. Okay, that's the best way to put it. When you run the program, you have to supply command line arguments, and I'll just do it once for so that you guys know what to do when you run this program. The instruction that I'm providing right now, obviously works in online GDB. But if you want to learn how to do the same thing in code blocks, there's a way to set up those arguments in code blocks too. So if you have used code blocks before, you probably kind of know how to do it. Yeah, I can illustrate how to do it in code blocks too. So give me a second here. I'll do it here first, and I'll do it one more time in code blocks. All right. So what I'm going to do is to set up a breakpoint at the subroutine where I need to actually write my code, right? And make sure that the language is selected to be just regular C. And then I just go ahead and debug the program. So when you hit debug, the program, it will try to compile the program, and oh, okay, I forgot to pound include parse. Okay, that's my fault. I'm gonna pound include it, and then I'll put this back into the text channel. So give me a second here because I forgot to put in the content of parse. All right, that's my oversight. All right, so this is on the side, and then just paste it here, and that's it. So there's parse, and I have to make sure that the pound include is removed, because that's the one thing that online GDB does not do, is you cannot have multiple files, not even your own header files. So everything has to be included in the same source file. At least that's in the past. If they have improved it, and make sure it's and it's better now. I do not know. Okay, so I'm not saving this file. Yeah, go ahead.
I know that Replit allows you to have multiple files.
It does?
It does? Yeah, it does.
Okay. Now, does it have debugging capability like GDB?
I don't know. I've never tried. All my programs run perfectly on the first try. They're pretty simple.
Oh, okay. All right. So I'm going to recopy this into Discord. So give me a second here. And I'm gonna reattach another file in Discord. Alright, so it's in double one main 1.c. Alright, so there's that one. I forgot to test it first, so I'm gonna pin it first, and then I'll go back and test it. Alright, so I'm back to online GDB. So I'm gonna debug the program. Hopefully it will compile this time. And nope, it's not one to compile, but it's giving me the same error when parse should be here already. And it's giving me a, maybe I need to click. Nope, that's not it. That is interesting. Because the debug and run button are both connecting to server. There we go. Alright. So I wasn't connected earlier, but parse is now in the source code, and the program has just compiled. So it just took a little bit of time, that. Okay, I have no idea what just went on, but it did take a little bit of time. So I'm going to put my breakpoint back into here. So if you're running it in online GDB, this is how you run the program. You have to say R, which is the abbreviation of run, and then you have to supply the command line arguments, which is -n, and then give it the base 10 scientific notation that you want to use to test your program. So in this case, I'm going to use like 2.34e. And remember, this is about using a negative exponent of 10 in scientific notation. So I'm going to give it like -12. Okay. So the value that I want to represent is in base 10, 2.34 times 10 to the power of -12. And then I press the enter key. And now the program gets to the breakpoint. And at this point, I can now, you can see GDB is pretty smart. It would give me the call stack for one thing. It knows where the breakpoint is. So at this point, you can use all the debugging tool or the commands in GDB. If you're using code blocks, you can use all the debugging tools in code blocks, or whatever IDE you want to use. You can basically use that to examine the local variables, the parameters, and so on and so forth. Alright, so I got a message. Do we need code to parse the different parts? It's already parsed for you. So let me show you what I mean by that. That is already parsed for you. So I'm gonna move the border up a little bit, because at this point the source code is actually not that important. So I would say print, there's only one argument, which is pn. So pn is a pointer. You can see it is a struct number pointer. So if you want to know exactly how the struct is defined, you can go to the source code. It is defined like way up in the source code. But you can always just say print whatever pn is pointing to, and that will give you the entire structure. So you can see how the mantissa is already parsed as 234, which is an unsigned 64-bit number. EXP10, interestingly, is not -12. It is -14. It's -14 because of one of the concepts that you have learned, or at least encountered, in one of the earlier labs. Okay, because if my mantissa is 100 of what it used to be, then I need to decrease the exponent of 10 by 2 to compensate for the change in the mantissa. So that's why the mantissa is 234, and the exponent of 10 instead of 12 is now -14. So I'm going to let somebody in first. And now I'm back. Alright. So that's already parsed. So you don't have to do the parsing, because I know writing parsing code is fun, okay, but that's not the what I want you guys to practice. So so the parsing part is already done, and now the whole point is we want to change the members of this structure until it meets the requirement as stated in the homework assignment. So let me go back to the homework assignment and look at the description. So this is the description of the homework assignment. So the first part, the first two paragraphs, basically just talks about, how do you get the source code. If you want to use code blocks, use this link here. If you want to use online GDB, then you have to use the file that I have pinned in today's text channel. So the idea is the value is always represented by the mantissa, which is a 64-bit unsigned integer, times 2 to the power of the exp2 member of the structure, times 10 to the power of exp10 as another member of the structure. And I want this value to be preserved as much as possible. Okay, so I can move things around. I can change the mantissa, I can change exp2, I can change exp10, but the idea is I would basically nudge these terms so that v is preserved as much as possible. So that's kind of the objective of your program. And then furthermore, I have these constraints or requirements. The mantissa should end up as a value that has bit 63 set. Okay, mantissa is a 64-bit unsigned integer. So I know some people are going to ask immediately and go like, so how do we do that? I'm going to let you guys research that a little bit, okay? Because, and the idea is you can use the bit shift operator. That's one way to do it. You can use a hexadecimal constant, okay, and see if the mantissa is greater than or equal to that quantity. And then I'll address the issue in the text channel in just a little bit. Let me finish explaining this part first. So so that's kind of, I want you guys to find out how to do this. Okay, it has to do with your understanding of the underlying representation of a number, and how do we make sure that we just check whether bit 63 is a 1 or 0. When I use the word set, it means it is a 1, and if I use the word cleared, it means it is a 0. exp10 should be a 0 when your program is done, when your subroutine is done. exp2 can be any integer. It is signed, so exp2 can be positive, it can be negative. The represented value v should be preserved as much as possible, which is something that I mentioned earlier already. So the rest really is instruction of how to run this code in code blocks. And I'm showing you today how to run this code in online GDB. So between the lecture, what we are doing right now, and the text instruction in the homework itself, the lab itself. And by the way, this is not something I expect you to get done today, during the lab time. I would hope that most people will start on it today, so that if you have questions, you can ask. But it is going to be due next Tuesday, right before lecture. So you have basically close to a week to get this done. Okay, now I'm getting back to the text channel to try to address the issues. Okay, so with Alexander, Alexander probably did not set a breakpoint. So the program just ran entirely and exit normally, so that because your subroutine is not doing a single thing, that's why it just exited normally. In other words, if I go back to GDB, in here, if I continue execution, that's exactly what I get too. It says inferior one, process blah blah blah, exited normally. So that's what happened with Alexander. There was no breakpoint set. That's why. And then Shaheen is making a point that this is a 1-week deadline. Yeah, well, what usually this translates to is on next Monday at about 10 p.m. or so, I will have like a bazillion messages on Discord, and I'm just gonna go to sleep and wait for Tuesday at 11 o'clock when my office hour starts. So you guys know already what I'm gonna do, and you might want to plan how to do this homework accordingly. There you go. Hmm. Well, you just have to plan your time accordingly. Pretend the homework assignment is due on Monday, and get started earlier and start to ask questions earlier so you don't have to push everything until the day before or the hour before the homework is due. Yeah, this one is kind of interesting because it's combining things that some of the stuff that you have learned through the labs, and then you have to kind of put it all together to get this program to work. All right, so without any delay, we are going to take a look at, but how do we do this, right? So that's kind of what we're going to do today, is for me to explain the logic of the code that you'll be writing of how to get this process done. All right. So first thing first, the first thing we'll do is we're gonna stop this program. All right. So click debug button to start program in debug mode. All right. So we're gonna debug it again because it timed out. Well, we did run the program to completion, so it didn't exactly time out. We just finished running the program. So when you test the program, you might want to test it with a smaller value. So you'll do a run -n, and this time with 1.23, or you can even use negative numbers. It will just change the sign member of the structure, which means you don't have to deal with it at all. So we'll do a 1.23 e negative 60. Okay, so this value is pretty small, okay, but it's not so small that it cannot be represented using a 64-bit double precision floating point number. So I run this code, and we stop at the breakpoint again. So you can see this line is grayed out, or it's gray, because it is indicating the program has executed up to this point. And now we do a print, and you don't have to spell out print, okay? P is sufficient for GDB to understand that you want print. And we print the argument, which is pn. And in fact, I print whatever pn is pointing to, which is kind of important. So we see the sign is a 1 because the value being represented is negative. The mantissa is 123. Now, this is displayed as 123 in base 10 only because GDB assumes that we want to read numbers or values in base 10. But internally, the mantissa is already a 64-bit unsigned number. Okay, so you don't have to worry about, but this 123 is still in base 10. How do I do the conversion? Nope, nope, nope. It's already done. Okay, the mantissa is a 64-bit unsigned integer. EXP10 this time is negative 62, and then EXP2 is initially 0. So this is your starting point. Okay. So what we're going to do is we're going to increase EXP10 by 1 so that we'll do it in a loop. Okay. So we need a loop at least so that EXP10 can increase by 1 whenever the condition is okay. But then you will say, but if we are to do that, don't we need to do something about the mantissa? So we'll go ahead and find out how to do that. Alright, so Alexander said, how do I set up a breakpoint? You just click next to the line. Okay, so you just move to whatever line you want and click on the left-hand side of the line number itself. So it's a toggle. So if you click on the line that already has a breakpoint, it removes the breakpoint. And since I'm on this specific breakpoint, it doesn't let me remove it. But you can, if it's on a different line, I'll pick a different line here. If you one click set it here, and the other click would clear it. But since I'm on this particular breakpoint, it doesn't let me remove it because I'm on it right now. Alrighty. Okay. Well, there's no beginning and end. I mean, setting a breakpoint on line 114 is the same as setting it on 120 because I don't have any code inside this subroutine. So when you start to insert code inside, then you'll be able to set breakpoints on those individual lines. All right. So how do I set up watches? I believe you just, well, you can always learn how to add a watch point. Just kind of Google how to add a watch point in GDB. So all the command line GDB stuff still works here. Or you can just say help watch. There you go. Just say help. Whenever you have an issue, something you want to learn in GDB, just say help. You can always say help break. It will tell you how to set up breakpoints. And so on. I mean, GDB is well documented. Okay, there are tons of resources out there for you to Google and read about. Okay, so it's just learning how to use that tool. Okay, cool. All right, so back to the main topic. Okay, so let me print star pn again, asterisk pn. There we go. So the idea is I want to be able to increase exp10 to -61. Okay, let's not be ambitious and just let's not be ambitious like I want to increase the exp10 all the way to 0 in one shot. That's not what we're going to do. We want to increment it just by 1 each time. But when you increase exp10, you're changing the value, right? So you have to divide the mantissa by 10 so that it kind of counteracts the change of exp10. But it becomes a problem because mantissa is only an unsigned 64-bit number. When you divide 123 by 10, you only get 12. So you have an error now because 123 divided by 10 should be 12.3. But instead, you're only getting 12 because it is an unsigned integer. And also, by the way, in this entire program, you're not supposed to use double or float or any math functions that relies on double or float. So you can only use integer math in this entire program. So you cannot use log, you cannot use power, you cannot use any of the math functions. No truncation, no rounding, no floor, and so on and so forth. Unless it is implicit, which is something that we're going to rely on. Alright, so now we're going to switch to the tablet, the whiteboard. And I'm just looking for the viewer. Okay, there we go. Alright. So we'll go ahead and look at the math of this problem. So we have 1.23 initially times 10 to the power of -60. And because everything needs to be represented by integers, signed or unsigned, internally it is now represented as 123 times 10 to the power of -62. So the value is being preserved, okay? And the idea is we want to only use integer math to do this entire process. So now we look at this and go like, I would like this to be something times 10 to the power of -1. But to do this, I'm going to have to divide 123 by 10. And the problem is, when you perform 123 divided by 10 in C, it is understood as an integer division, which is the only kind of division you can do. You cannot cast things into double in this program. So that means instead of 12.5, you only get 12 back. So when you compare 12 versus 12.3, which is what the real answer is supposed to be, you have an error. You have an error that is about, it's a little bit less than 3%, but it's still there. So that means, this approach is not going to work very well. I mean, it does work, but it's not going to work. It's not going to work very well. So what we'll do today, or what we'll do now, is we're going to go back to the notes. So we'll go back to the notes. Okay, so we'll open a new tab. I keep losing tabs this way. Oh, by the way, there's a really cool plugin or extension for Firefox. Let me show you what it looks like. It's this guy here. It allows me to search all the tabs that I have. and it's really, really cool. Rip off logo. Hmm. But anyway, it's really cool because if I want to find out where my Outlook tab is, it finds it right away, and if I click on it, it will put me to the window that has that particular tab. So it's really helpful for people like me. I have like 7 tabs open, and each one has 20 or 30 tabs, so it becomes kind of difficult for me to locate things. Yeah. So anyway, really kind of cool tool, useful. All right, so Andrew, okay, we're getting to it. We're getting to it, Andrew. So let me go to the notes first, so that everybody knows where we are at. So we are looking at floating point number representation, and we are looking at conversion from base 10 scientific notation to double. All right, so we'll get to your point, okay, Andrew. We'll get there eventually. So the first thing is we're going to be focusing on 5.2.1. Okay, so 5.2.1, exponent of 10 is less than 0, so that one is directly applicable to what we are dealing with here. However, the earlier section is also important. So we'll kind of go through the earlier section a little bit, and then we'll get back to section, the section that we really need for this class. All right. I'm just scanning through this to find which part of this is going to be super relevant. I mean, you guys are supposed to be reading this entire thing. I'm just locating the part where I really need it. All right, so there's this part here. Okay, the round of n divided by d is the same thing as the floor of n divided by d plus 0.5, which is then the same, just using algebra, the same as n plus 0.5d, the whole thing divided by d. So when d is a number that is even, which is wholly divisible by 2, then it's kind of handy, okay? Because if d is divisible by 2, then 0.5d becomes just an integer. So now we are looking at n plus some kind of integer divided by another integer, and take the floor of that. But integer division is automatically doing the floor, and that's how we can do rounding without needing to convert something into a double first. Okay, so that's kind of, I hope this connects with some of the activities that you have done in the lab before, right? Because, one of those questions is, okay, let's compare the round of something divided by 10 versus the floor of that thing divided by 10. This is where that thing is coming from. And now we are on section 5.2.1. So what we want to do is we want to make the mantissa as big as possible before we do the division by 10. Because when the mantissa is really, really big, yes, when you divide it by 10, you still end up with an error, but the error will be smaller. Okay, so let's go back to the tablet and see what we're going to do in this case. So in this specific case, this is not what we want to do, because it will end up with a pretty big error, which is not something that I want to do. So what I want to do is to say, this would be the same as 123 times 2 times 10 to the power of negative 62 times 2 to the power of 1. Okay, and then somebody's going to say, but where is that 2 to the power of something coming from? Well, it has always been here. It has always been here, I just didn't write it. Because you can always assume that there's an exponent of 0 associated with the base of 2. So initially I did not write it because it didn't seem to be useful, but now it is useful because I need this to counteract this. Okay, Take it back, it is -1. Okay, yes, so Nathan is correct. It is supposed to be -1 because I'm doubling the mantissa. So now I can look at the mantissa and go like, let's not look at it as 123 times 2. Let's look at it as 260. Oops, I cannot do multiplication. Let's look at this as 246 instead. You look at this and go like, well, but eventually you still have to divide it by 10. So when we look at 246 divided by 10, you're still losing that 0.6. Okay, even though it's the same error margin, right? So we'll go ahead and increase 246 again, or double it again. So if we multiply this by 2, we have 2, 9, and a 4. So we have 492 times 10 to the power of -62. Yes, I haven't done a single thing about the exponent of 10, because if I do a division by 10 right now, I will still be dealing with a relatively large error. And now the exponent of 2 needs to be adjusted to -2 because I have multiplied the original 123 by 4 at this point. So I need the exponent of 2 to be -2 to counteract the multiplication to the mantissa. So you can probably tell the next thing I'm going to do is something super boring, which is to multiply 492 by 2 again. Okay, so we'll do something boring a little bit, and then we'll find out how to not do something so boring by hand. So we have 2 times 2 being 4, 9 times 2 is 18, and then 4 times 2 is an 8, but because of the carry, we have a 984 times 10 to the power of -62 times 2 to the power of -3, and so on. So now the question is, when are we going to stop? I mean, you can definitely tell that, if I multiply 984 by 2, it's going to be, what, 1900 something? Exactly. So Nathan is right on the text channel, until we run out of bits. But how can we tell that we are running out of bits? So that becomes the next question, right? So, okay, so what is the condition, okay, that becomes true when we quote-unquote run out of bits? Why does it have to be below 1000? Remember, the mantissa, which is this part here, is a 64-bit number. And 64-bit number can have up to 19 digits in base 10. I mean, that's a huge number. But eventually you will run out. So the question is, how do you know that you're running out? That is correct. Omar is correct that eventually the mantissa only has 52 bits, but during the conversion, we're going to use all 64 bits because it's easy to lose bits when we need to truncate it or when we need to round it. But during the process of converting it from base 10 to base 2, we would like to preserve every single bit possible so that we have minimal error in the process. So Omar is correct, but we're not going to limit to only 53 bits during the conversion. We'll do that, until when we're getting to the end and we go like, yes, this is the 64-bit mantissa, but we cannot represent the 64-bit mantissa. We can only represent 53, effectively 53 bits out of the 64. We'll get rid of some bits at that time. It's easy to lose information, but once you lose information, you cannot gain it back. So that's kind of the point. And Aaron is right. That is why we stop at bit 63, not 64, because we count from 0. Yes, it is better to use bit shifting. So now is a good time to talk about what is bit shifting. So let me ask the class, how many people were introduced to the concept of bit shifting in CISP360? So we got a few, and we got no, we got no, we got another no. So now the question is, who was your professor? Alright. So now we need to talk about the concept of bit shifting. Bit shifting is pretty easy. Let me think about how to explain it. So did Dixon talk about bit shifting? Okay, he did not. Okay. Alright, well, that's okay. I can explain that. And of course, I have lost track of where the... Yep, there we go. Okay, so we're going to go back to debug mode again because it has timed out. And this time, I'm just going to look at expressions. This is another way to use GDB. Because GDB understands C notation, expressions in C. So if you want to just kind of experiment with certain things, as expressions in C, this is a great way to do that. Okay. So we'll look at 1 left shifted by 0. It's just 1. 1 left shifted by 1 is 2, because what bit shifting is doing is it's looking at the binary representation of a value, and the shifting means we are a left shift means we are putting new zeros in on the right hand side, and then we are moving all the existing bits to the left hand side by whatever position that you're shifting. Okay, so this the right hand side of the operator specifies how many bits you're shifting. That is the number of positions that you are moving the existing bits to the left hand side, and it will basically insert the same number of zeros from the right hand side. Alright, so I'm just checking the text channel right now. Okay, I cannot comment on any advice about other professors, so I cannot say or do anything about it. Okay, so the nice thing about GDB is it understands base 10. Okay, obviously, it understands hexadecimal, which is this is something that a C compiler understands also. But the best part is GDB also understands binary. So this is the great thing about GDB. So okay. No. Okay, I just click some keys unintentionally, and that's okay. That's okay. Not a problem, because I have the program saved on the other side. This happens, right? I mean, so the idea is be prepared. Just like that song in Lion King, be prepared. I cannot sing. You don't want to hear me sing. That would be terrible. That would be like punishment. People who cheat in my classes will have to hear me sing as part of their punishment. And nobody is going to cheat. Alright, so we'll go back to debug mode again. Alright, there we go. So we're going to print, I'm just testing which, I cannot remember whether it's 0B or 0T, so we'll test 0B first. And it is 0B. Okay, very good. So I can now print 0B. So we'll try something first. Okay, so this is not, I'm not teaching you anything about computer architecture or assembly language programming, but I'm teaching you something about how do you get to learn a tool, right? So if you know that 101 is 5 already, then you try that out, okay? You make sure that you're getting back 5 so that you understand, oh, okay, so 0B is indeed the prefix of a binary number. Because if you use 0x101, it is going to be 257, because 100 in base 16 is 256. So when you add 1 to it, it becomes 257. So this is sort of how you can use an interactive engine like GDB to kind of test out features in the programming language. But 0b, remember, is not a C syntax. It is only usable in GDB. So in your program, you cannot use 0b as a prefix of a binary number, but when you're debugging, you can use it. So the next question is, but it doesn't help when the output of print is in base 10. Okay, so I want the output of print to also be using base 2. Okay, that's going to be the next thing that we want to do. So you might say, I'm just going to say help print, and that will tell me how to format the output of a number, a numerical value, an integer value in base 2. And when you print it, it doesn't really quite show you that. Okay, it says, exp may be preceded with /fmt, where fmt format is a format letter but no count or size letter. And then the last part of it, this is the favorite thing that I like about online documentation, is cx command. So you say help x, and it gives you a whole bunch of blah blah blah, and then it tells you that the format letter to specify binary is T when you print it. Yes, I know this is like a little bit inconsistent. Okay, escape, this is what I did earlier, is not to have the cursor blinking, so the my keystrokes are not being captured by the GDB interaction terminal. It is actually captured by the browser itself, and that's how I lost the previous session. So print /t, so that's printing something in binary. So you can print something that you know what the binary representation is, like 5, right? Because 5 is supposed to be 101 in base 2, and it does give you back 101. So now that we have a way to print and specify values in base 2, it is super handy because now we can test bit shifting, expressions. So we'll start with something simple. Okay, we'll start with 101. Let's shift it by 2 bits, something like that. Hey, that works, right? So now we can start to do something a little bit more complex. Just give it a whole bunch of zeros and ones, and then shift it by maybe a little bit more bits, like 6. So if you count the number of zeros, inserted from on the right hand side, and you check the rest, you will see the effect of left shifting. So do we have any questions about the left shift operator? No questions? Yeah, it does have autosave if you sign in with an account. So to answer Zoe's concern, if you sign in using your Google identity or whatever, it allows you to save the file. So it's actually pretty cool. But you don't need to, because I know some people are concerned about their privacy and whatnot, and they don't want to sign in using the Google identity to all kinds of websites. That's okay. You don't need to. I mean, for the most part, if you're concerned about losing your program, you can always just kind of copy and paste it back into your text editor in Windows or Mac OS X or Linux. That's the other way that you can kind of back up things. Does it delete 0b? So 0b is not being used as a prefix, so it is understood that this is a binary number because of the use of the /t. There you go. So that should answer Mohammed's question. Alright, so now that we know what bit shifting is doing, okay, let's relay that back to what we're doing here. So multiplication by 2, each multiplication by 2 is essentially is basically shifting 1 bit to the left. Okay, that's basically all that it is. And if someone says, I am not convinced, well, you can go ahead and print 123 shifted 3 times to the left, and compare that to the binary representation of 984. Okay, that's one way to kind of check it out and see whether that works or not. Okay, all right. I'm just checking the text channel to make sure that I'm not missing anything super important. Okay, so anyway, so now the question is, how far can we go before we run out of bits? All right, so this is going to take a while, right? Because you can say, let's take a look at 123 as a base 10 number. Okay, it's got, sorry, as a base 2 number. All right, this is what it looks like. What about this number left shifted one time? Okay, twice, 3 times, and so on. Okay, so now the question is, but how do I know that it is out, right? Someone is going to look at this and go like, well, 123 is the largest is okay, the smallest base 2 number, the smallest power of 2 that is greater than or equal to 123 is 128, which is 2 to the power of 7. So if we subtract 7 from 63, that should tell us how many times we can left shift this, okay, and still have everything fit into 64 bits. So if you're reasoning along this line, you're correct, okay, you are correct. But to understand that 123, is closest to 128 as a power of 2, that requires log, okay, which is not something that we can do. Now, if you say, but I can use a table lookup to do this, well, yeah, you can. Yeah, sure. I mean, you can use a table to look up things and find out how many times you can shift. But you can also use a loop, right? So you can use a loop to basically say, double this. Check. We are not there yet. Double again. Check again. Are we there yet? No. Let's double again. But remember, every time you double the mantissa, you have to decrease exp2 by 1. Because otherwise, the value being represented is going to be changed. Okay? So now we're going to go back to the module, because the module actually describes how the logic is going to work. So it says right here, as long as m, which is the mantissa, is less than or equal to the largest numerator value divided by 2 minus 5, keep doing this. So now, to get back to the earlier question that somebody asked, I cannot remember who asked that question, but that was a good question, which is, what exactly are we talking about here? So the largest numerator value is the largest value that you can represent using a 64-bit unsigned integer. And I'm sure someone is thinking, how do we know what that is? Well, we kind of know what that is because we actually already talked about how to find out the largest value that a binary number can represent given the number of bits that we have allocated to the integer. We talked about that already, okay, in one of our classes. I remember that I wrote it on the tablet. Yes, I did. It is also in the form of one of the sigma notation in the notes. So we kind of know how to compute that value. You can also represent that value because you already know that in base 2 it's just going to be 64 ones, right? But you know that you cannot do a 0b and then 64 ones in the C program because 0b does not exist as a part of the C syntax. So you have to convert it into base 10, which will give you a 19-digit base 10 number. You can always just type it in. That works. You can also more easily translate that 64-bit number into base 16. Okay, so base 16 is just going to be a whole bunch of Fs. Marco is partially correct, just missing 1/2 of all the Fs. Because what Marco has typed is a 32-bit number with all the ones. So in order to have 64-bit all the ones, you kind of have to double the number of F's, right? Okay, so all of that works. There's one more method to do it. Yes, I really like to emphasize that there are always multiple things to do the same thing, and then you have to choose, one way to do it. Alright, so what you do is you look up stdint header. Okay, so the first one works. There we go. And just pick this one here. So this describes, all the things that are defined inside the header file. And because we are concerned about maximum values, right? I mean, you guys don't expect me to actually read documentation, from end to end. I mean, that's just gonna take up a lot of time. So what I'm gonna do is just looking for the word maximum. And here we go. We have a whole bunch of max. Okay. And how come it's not finding those things? Huh. Oh, maybe it's case sensitive. So let's look up max. Oh, because it's matching whole words. So we'll just match not whole words. Then it finds a whole bunch of choices. So you can see all of these things here, and you can see they have int, okay, and then they have uint. So can anyone guess what the u is representing? It's actually already staring at you in the face. Unsigned, exactly. Unsigned has a u in front of it. Okay, so you know that uint underscore max, something max, is what we are looking at. So which one are we looking at? What about this one? Maximum value of exact width unsigned type. Oh, okay, so this is what we need, right? So we just copy and paste this constant name or macro name into the program. And then you find out that the compiler is going to give you an error and say, hey, there's no such definition. So why is that? Do you see how the end is italicized? And what do you think it signifies when something is italicized when everything else is not? We got a few people typing. Nope. It is, yes, it's a token basically. It's a placeholder. Okay, it is a placeholder. It is here to say I need to be substituted with something else. And what do you think that something else is supposed to be? Exactly, the width of the integer. So I'm not going to give you the full name of the constant that you can use coming from standard integer.h, because I think you can put all of those pieces together and figure this part out. There you go. Alright, so getting back to the notes. So now we know how to specify this thing. And how can we have to divide it by 2 minus 5? What is that doing? Well, the division by 2 is needed because if m is not less than or equal to this number divided by 2, forget about the minus 5 first. Okay, the minus 5 we'll deal with it later. Just focus on the largest unsigned 64-bit value divided by 2. Just focus on this one first. Because if m is already greater than the value, then you can no longer double it. Because if m is already greater than or greater than, not equal to, but just greater than the largest unsigned 64-bit value divided by 2, if you double again, then you won't have enough bits to represent m anymore. Does that make sense? Does that make sense? That we want to stop the loop when m is not exceeding the largest numerator value divided by 2. Well, when it is, we stop when it is just greater than that value. Okay, very good. Excellent. So now we deal with the minus 5. What is this minus 5 coming in? I mean, that just looks really odd. That's because when we eventually want to do a division by 10, this is what we want to do. We are going to add 5 first to m. Then we divide the sum of m, which is going to be a huge value. Remember, it's going to have bit 63 enabled, turned on. Okay, so m is a really, really, really large value, plus 5, which is insignificant by comparison, and then the whole thing divided by 10. Why do we do this plus 5 and then division by 10? It has to do with the rounding trick that we talked about earlier, which is also discussed in one of the labs. Okay, because eventually what we want to do is to round n divided by 10, right? That's what we want to do, which is the same thing as n, which is a huge number, divided by 10 plus 0.5, because these two are the same. When you're rounding versus flooring, you're just shifting things by 0.5. That's basically what that means. But when d is 10, then you can use the trick and go like, oh, okay, we can just add 1/2 of 10 as part of the numerator and then maintain the denominator. That is the trick that we are using, so that we can do everything using just integer math. Because m plus 5 is just integer addition, and then when we divide that sum by 10, that is also just integer division, which already has built in the floor, which has the flooring built into it. So we don't really explicitly use floor because it's already built in to integer division. That is why. Okay, so this is all kind of, I hope this is all kind of coming together, because we did a few labs, so that we kind of get familiarized with exponents and stuff like that, and then we did some lab based on rounding, kind of like this. So after you do this division by 10, then you have then you can add 1 to E10 or EXP10, because at that point the mantissa is about 1/10 of what it used to be, which is still gigantic and huge. And only at that point you can say, okay, since we divided the mantissa by 10, then we have to increase the exponent of 10 by 1. But remember, EXP10 was negative 62 in our example, so now it becomes negative 61. Woohoo! We got a little bit closer to 0. Then what do? Just do the whole thing again. Make m as big as possible again, because once you divide m by 10, then it's no longer going to be greater than the largest unsigned 64-bit value divided by 2, so it's not going to be like that anymore. So that means you have to go through a few doublings before you can divide it by 10 again. And you just keep doing this, and then that, and then this, and then that, and then this, and then that, until your EXP10 is 0. Then you can go. Then you're done. Almost. So is this all kind of making sense? Okay. All right. Cool. So that's kind of what your lab is going to look like. Even though the concept is easy, you still have to formulate the logic that I have just described into actual logic. And I'm just looking at the time. We still got about 15 minutes to go. So in terms of implementation, to address Zoe's concern, we're gonna illustrate the logic more or less using a spreadsheet. So let me see. I can use my own spreadsheet here. Okay, the idea is pretty simple. Okay, I'm just using a spreadsheet to illustrate an idea. Okay, so you don't really need access to the spreadsheet itself, but the concept of the spreadsheet is what you need to kind of understand and incorporate into your own program. All right, so what we'll do is we're gonna take a look at 123 on one column. and then we look at how many times the offset of exp2. Okay, and the next row is just going to be whatever the previous row has times 2, and then this one is just whatever the previous row has minus 1. Yeah, that's what I'm doing right now. I'm doing one example, which is 1.23 times 10 to the power of negative 62. 60, negative 60. So I'm working with that example, but the mechanism to do this, is kind of like this. So what you're going to do is you're basically just doubling, okay? But then you have to compare the value to the largest integer, blah, 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 divided by 2. So you're going to have to say, okay, I want to, compare this value and see whether it is still less than or equal to 2 to the power of 64, the whole thing minus 1. Okay, so I'm just gonna do this. Okay, so you go like, wow, this might take a while. Remember what I said earlier? Because 123, the smallest power of 2 that is greater than or equal to 123 is 128, which is 2 to the power of 7. So when you subtract 64, when you subtract 7 from 64, you get 57. So I think that is the number of times we have to shift it. So we just have to use what, 57? And I'm going to exceed it a little bit just so they can see how the condition changes. So, okay, 58 times. Okay, so we have to shift it 58 times. And this is the last time that the condition is true, which basically means, when it gets to this point, it's time to get out of the loop. Okay, so when we get out of the loop, we end up with this value. So we'll go ahead and get rid of this row here. So we look at this value, and this turns out to be it turns out to be the largest mantissa that we can use. Okay, after a whole bunch of doubling before we run out of digits in the 64-bit unsigned mantissa. So this is when we're going to do the plus 5 and then division by 10, right? So we'll go ahead and do that math. So we say, okay, we want this value. Okay, take it back. So we want this value plus 5 and then the whole thing divided by 2. So this becomes my new mantissa. And if I want to track exp10 initially is negative 62, and now it becomes negative 61. And obviously the exponent of 2 would still be the same as before. Okay, so when you look at the value being represented, that has not changed at all. In other words, if I were to compute the value, okay, what is the value? The value is whatever the mantissa is times 10 to the power of whatever is in column D times 2 times 2 to the power of whatever is in column B. This is the value, okay? And we can see it is 1.23 times 10 to the power of negative 60. I forgot about the negative side part of it, but that's not important. So when we copy this formula to this form here, uh-oh, I did something bad. Forgot about something. What would that be? Oh, this is using the wrong value for the, nope, it's division by 10, not division by 2. Darn. Okay, forgot about that. Aha, nobody caught me earlier. Okay. So anyway, I made a mistake. because this is supposed to be division by 10, because we're supposed to divide the mantissa by 10, because that's the only way I can increase the exponent of 10 by 1 is by dividing the mantissa by 10. So, and I mistakenly used division by 2 instead of division by 10. So anyway, you can see how the value is now preserved. So now the question is, how many times can I double this, until it cannot be represented anymore by a 64-bit number? So once again, I use the same approach. I just basically say, let's double. And if this is still okay, let's double again. And if this is okay, let's double again. And now it is, this particular value is using all 64 bits already. So that means, okay, we cannot double anymore. So that means it's time to do the division by 10 again. And this entire row is doing the division by 10 and then adjust the power of 10. So this part is incorrect because it is supposed to be this plus 1. So you can see how the value is still preserved. Okay. And now what do? We keep doubling and then divide by 10, double, 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 divide by 10, double, 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 divide by 10, and so on. So I think that is my way of addressing what Alexander has written in the text channel. So for those of you who want to kind of carry this a little bit further, the time is 42, so we got 8 minutes. We can spend the next 8 minutes doing all of this stuff here. Yes, that's kind of the idea of why we want to write a program, so that we don't have to do this by hand. That is just a waste of time, right? So now we look at this and go like, okay, we can now divide it by 10. But I do want to illustrate a few, 1 or 2 points here. It's kind of important. Okay, so we do this, and then we double again, double the mantissa. Okay, so we double, and then we double, and then we double, and then we double. You go like, wait, hold on a second here, Tack. We only had to double 3 times before, and then 3 times over here. How come this time it took 4 times? Yes, we basically keep doing this until EXP10 becomes 0. Where's my -5, -5 in my example? It only happens when we do this. So you can see how there's a +5 and then the whole thing divided by 10. Oh, you mean the comparison? Yeah, I didn't put it here because it is somewhat insignificant. But if you want to put it here, you can always do this whole thing and then another -5. There we go. It doesn't really change in most cases because it is unlikely that you run up to the value that is really just 5 away from the largest integer. But that's kind of, you can see how that didn't really change all the conditions. So yes, you're correct that I forgot to do the subtraction of 5, but at the same time, it doesn't really, the bug doesn't show up, except for certain crafted values. Okay, so if I were to test your program using those crafted values, it might fail because you forget about the -5. Because in those cases, that add 5 is going to exceed what a 64-bit unsigned value what can be represented by an unsigned 64-bit value. But in most cases, that is not going to happen. All right, so getting back to the question here. Okay, so even with that -5, as the value to compare to, put in, you can still see that, we only need to like double 3 times, and this time we have to double 4 times. Well, that has to do with the value of 10 compared to powers of 2. Because 10 is between 2 to the power of 3, which is 8, and 2 to the power of 4, which is 16. That is why sometimes you only have to triple it. I mean, you only have to double it 3 times, which is the same as multiplication by 8, in order to bring the mantissa back up to be using all 64 bits. But other times you need to double it 4 times in order to get the mantissa to be the largest value, to use up all 64 bits for the mantissa. And Chris, yes, you should use the minus 5. It is max divided by 2, the whole thing minus 5. Okay, we got a few text messages coming in, so I'm gonna wait a little bit. Alright. The minus 5, okay, let me get back to the browser. Okay. So the minus 5 is because we don't want this plus 5 to exceed what a 64-bit number can represent. So we have to take this particular plus 5 into consideration, and basically say we want to make sure that after we double m, we will still be okay with this plus 5 over here. So that's what the minus 5 is for, is because we have to plus 5, we have to add the mantissa by 5 before the division, and we want to make sure the mantissa plus 5 is not going to exceed what a 64-bit number can represent. Okay. Alright, so Omer is asking, what am I doing in these subsequent calculations? Well, I mean, if you look at, okay, let me go back to the spreadsheet first. Right there. So when you look at the power of 10, it's still negative 61. I mean, we are not done yet because we want this to be 0, right? But we cannot just keep dividing this value by 10 because it is no longer using all 64 bits, which means if I divide this by 10, then I'm going to lose precision. So that's why I have to bump it up all the way back up to use all 64 bits before we divide it by 10, which then allows us to increase the exponent of 10 by 1. But then it won't be using all 64 bits again, so we have to bring it all the way up until it uses all 64 bits. Then we can divide it by 10 again, and then we can increase the exponent of 10 by 1 again. Yeah, okay, that's cool. If you have a mantissa of 0, your loop should exit right away, because that's what we're looking for, is when the mantissa is 0, we should get out of the loop. So your loop you should stay in the loop only if the exponent of 10 is less than 0. Omar is asking, so the comparison is not divided by 2. No, it is divided by 2. So the comparison is compared to the largest number that can be represented using 64 bits, and oh, okay, did I make a mistake here? Did I forget to? I thought I fixed that. Oh, okay. Yep, I'm forgetting the division by 2. You are correct, Omar. I forgot. So we have to remember to do a division by 2. And then subtract the 5. Let's see. There we go. Yep, so all of these is going to off by 1. The number of times we have to do this is going to be off by 1. You can see how it is off by 1. But that's okay because we can now just basically. Okay, first of all, I have to copy that here. Okay, I'm just gonna. I'll catch up with the text channel after I'm done with doing this. It's okay, it will all work out. Um, because I'm gonna remove one of the rows, and once I remove that row, everything will be okay again. And I think this one may be okay too. It's hard to say. Alright, so it looks like everything is not working anymore. But if I remove this row, then everything should work again. So we'll delete this particular row. Oh no, crap. It doesn't like that. Well, it's okay. We will change this manually. So this has to be referring to A58. And then this is going to refer to B58. There we go. So we got everything back again. Alright, so I'm just trying to catch up.
I believe you're missing one truth value, are you not?
Huh?
Doesn't line 60 need a truth value?
Which one?
60C?
60. C60?
Yes.
C60 does not have a condition because C60 is representing the division by 10. So the division by 10. So this is going to be true, right? Because after the division by 10, the mantissa is only going to be smaller, and it's going to be true, not false. If I were to extend it, it's just going to be true, but it's not important, for row 60, 65, and 70, because those particular rows are representing a division by 10, so that we can bump up exp10 by 1. Okay, so let me catch up with the text channel too. Okay. So Omar is right. Okay, we found, I forgot not just the -5. The -5 is not, the subtraction of 5 is not the big deal. The division by 2 is. And then Nathan said we double one more after we check the condition. No, that is not what we're doing, because this is signifying that we should not double anymore. So think about the loop, okay? It depends on what your loop is structured, how your loop is structured, but the false basically is saying don't go back to the beginning of the loop. Don't do another iteration. That's what the false is representing. True means the value in the mantissa is still too small. It is not using all 64 bits yet. False means, nope, it's all using 64 bits now, don't double anymore, because if you double again, it's going to run out of digits in a 64-bit unsigned number. Okay? Alright. And then we have Zoe saying the final answer, the number with false, but not the last number with true. So once again, the false is representing when we get out of the loop. So we do want this value to be in the mantissa before we continue after the loop. Okay? And then Jonathan says, wouldn't it cause an overflow in the program? Well, that's exactly why we are comparing to the largest value that you can represent using 64 bits divided by 2 and then the -5. Alright, so we still got a few more text coming in, and I'm just looking at the time. Okay, we are finishing this program, with doing it manually is just going to be a lot of chore. Okay, that's just going to be really chore-ish. I mean, basically what we're going to do is, we're just copying blocks of cells, right? Just copy it over here, and then the reference to the base 10 number or the base 10 exponent needs to be adjusted, because it's doubling 3 times most of the time, and then sometimes it has to double 4 times. So for the most part, it's just a whole bunch of copy and pasting of these cells until the EXP10 is increased to 0, which is exactly why we want to do this with a program. Seeing this as a spreadsheet is increasingly confusing. Information overload. Well, each row is representing what your program, what your code is supposed to do. And when you see repeating patterns, it's like, oh, we do chuck 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 clunk, chuck 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 clunk, chuck 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 clunk. That means we have a loop there, and then every clunk, okay, is something that we do after a loop. But the chuck 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 clunk is itself inside another loop, and we get out of that loop when EXP10, which is column D, becomes 0. Yeah, but we can't use log. That's the whole point. You cannot use log, because to use log, you need to rely on double representation, which is kind of defeating the whole purpose of this program. Because I want to do everything with integer math, so that this logic can be super fast with a processor that has no floating point units. Oh, algorithmic, not algorithm. Okay, gotcha. All right. With a spreadsheet, you can't see what is going on behind the scenes. How about this? I will upload the spreadsheet, so this way you can actually explore all the formulae being used in the spreadsheet. If anything else, I think a spreadsheet really illustrates how the loops should be structured. It depends on whether you can see that or not. So let me save it. Okay, so I'm going to save it and put it into the text channel, whether you like it or not. So how should we call this? EXP10 to EXP2. Okay. Doesn't want to save it. Oh, okay. I'm pointing to the path, thinking that I'm specifying the file. There we go. So this is really kind of broken, because okay, so I want to save it in the temp folder, but the name is EXP10 to EXP2. There we go.
Can you change the file type as well?
No. I know Microsoft Office can actually open Office documents, and so can Google Sheet. If you upload this to Google Sheet and turn on automatic conversion, it becomes a Google Sheet. And these formulae are so simple, Google Sheet can handle it. All right, fine. We'll save it in Excel format. This is like sacrilege.
Woo!
Yeah, go ahead.
Woo!
Huzzah! It's a celebration.
Okay, so XLSX. There we go. Save. See, even the program says, "Are you really sure? Why don't we just keep using ODF?" All right, so now I can upload it, and it is called EXP10 to EXP2. Hey, how come it's not found there? Where did I actually save the file to? I thought I saved it to the right place. Let's check file properties. Alright, so it's saved to it's saved it to my documents. Okay, fine. There we go. Okay, found it. Open. There we go. Alright, so I have just uploaded the Excel spreadsheet this time. You can upload it to Google Documents if you want to, or you can just open it with Microsoft Office if you have Microsoft Office installed. Yeah, exactly. So Anne Marie is correct. The conversion between between OpenOffice and Microsoft Office would kind of mess up formatting stuff. But since I did not use any formatting whatsoever, the formulae are fairly universal. The ones that I use in this example are fairly universal. Yeah, some of the functions. Interestingly, Google Sheet actually offers many functions that are missing in both LibreOffice and Microsoft Excel. At the same time, Google Sheet doesn't understand indentation within a cell, which is really odd. Okay, because they just don't do a whole lot of formatting. But in terms of text processing, especially regular expression, Google Sheet has superior functions when it comes to that sort of processing. All right. Yeah, the 0 1 versus false and true is just formatting. You can format 0 and 1 back into true false and the other way around. So it's not really that big of a deal. In other words, for those of you who prefer to see things as zeros and ones instead of true and false, you can go to this column and then go to Format and go to, I can't see very well what I'm seeing here. Format, number, format. There we go. So if you go to just regular number, then it all becomes zeros and ones with decimal points, obviously, in this case. Yeah, but that's the whole point. I mean, true and false is nothing more than just what label is being used to display the value of a cell. But if I switch back, it becomes true and false. I think true false makes more sense in this case because this is telling you whether you should stay in the loop or whether you should get out of the loop, which is my way of giving you a hint of how to structure your program. All right, so I think we are good in terms of having enough material to start writing this program. And once again, it's not due until Tuesday, next Tuesday. So let me release the homework first, because otherwise you guys cannot really get started. Alright, so the homework is called Negative Exponent, and it has its passcode too. So let me show you the passcode. Or at least I thought it had a passcode. Nope, doesn't have a passcode. So you don't need a passcode for this one. And it's due next Tuesday. And next Tuesday is not going to be in February anymore. It's going to be March. Okay, I'm too lazy. It's going to be March 2nd. Okay, so it's going to be March 2nd, and it's due right before the lecture, which is 5:30 p.m. Oh, okay, that won't work, would it? Having the until set to 19:05 is not gonna work. Alright, so March 2nd, 5:30 p.m. There we go. And click Save and Publish. So you should be able to access the lab now. I mean, you guys already have all the kind of really important stuff already. The spreadsheet is on Discord. The single source file is on Discord. So the rest, I mean, the homework assignment is really just kind of the description, which I have already mentioned. Back to the Future. Or we can be Time Lords. No. So to answer Chris's question, I mean, if you guys want to drop off from the uh, the live stream, it's okay. Because I'm kind of answering individual questions, but this question is good. Okay, um, to I think struct is needed because this is a C program. If number is a class, then you do not use struct. So I think this is one of the differences between C++ and C is when you're using C and you want to refer to a structure, you still have to use the struct as part of the name. I suppose you can use type def, to get rid of the struct. I mean, that's one way to get rid of it. But I'm pretty sure, the program does compile. And then Alexander is also typing. So I think now I can just kind of drop off the live chat, and also the live stream. So I'm gonna stop the streaming at this point. But I will, keep an eye on